Welcome to the dynamic learning hub of XLR at Andheri East. A prime spot conveniently located at just a 5-minute walk from LIC Andheri Metro. In our journey of over a decade, we have proudly trained over 2 lakh students. We have also been recognized by Deloitte, Silicon India, and other accreditation bodies. Experience learning like never before in our spacious and comfortable classrooms. With high-definition projectors and state-of-the-art acoustics in place, we ensure effective learning even to the farthest point in the room. The hybrid mode is a game changer as you can enjoy the benefits of a light classroom from the comfort of your home. Even if you happen to miss any classroom session, you can still attend the same session with the same trainer at the same time at your convenience, maintaining consistency in your learning progress. Wanna get started? Join us for a demo or career chat over a cup of coffee at our Andheri branch. XLR. We don't just train, we build careers.
Yes, so the collaboration with XLR was an excellent one. We conducted a Power BI workshop with Advanced Excel over a span of 3 days. The workshop was almost 12 hours long in total. Mr. Karthik, who was an amazing trainer, helped the students understand the concepts deeply. I am sure that the students will be able to apply these concepts in their careers as well as their daily lives.
The trainer, Mr. Karthik, was an excellent person where he explained in very detailed manner on how to give great insights using very complex data sets.
So it was a machine learning workshop. We learned a lot from the course and it was a great experience attending the workshop.
The trainer was very helpful. He had a hands-on approach with his teaching and it was fabulous.
This was a great experience for me. So I would absolutely love it if XLR and its team would come again to our campus and conduct more events like this.
It was a great course and it started from basics and took me to a great extent.
The experience of the workshop was really nice. The feedback from all the students was positive. They understood the concept. The workshop was also practical based with some questions. The experience with XLR was very smooth. They helped us in conducting the workshop smoothly right from the booking of the vendor and deciding the course till the distribution of certificates. In overall, this workshop was a success during our Technical Fest Atmos, and I thank XLR for being a part of it.
Good evening, all. Students, I request please inform your friends to join the session as soon as possible. We have very less participate today. Kindly inform your friends to join the session. Sir, good evening. I hope my voice is audible.
Yes, it is audible.
Good evening, sir. Yeah, thank you.
Good evening. So, shall I start?
Yeah, you can start, sir.
Okay. Thank you so much. Okay, there is a question regarding LMS portal login. Uh, Shushmita, can you please give a small brief on this?
Yeah,
Because
sure, sir.
already
What was the question, sir?
basically means after logging into the LMS portal, actually it is not showing any active courses. So that is the question.
Okay, fine. So, students, if you have any query related to LMS, I request please not to ask sir, because as he will be teaching the topic, even he will get the disturb. In the end of the session, I'll answer for it. Or else, I request please drop a mail to edl@xlr.com. We will help you out. If you are facing any issues on LMS or related to certificate or anything, you can just drop a mail to edl@xlr.com. I'm just pasting the mail ID on the chat. Yeah, you can
Yeah, yeah.
continue, sir.
Thank you. Thank you so much, Sushmita. Thank you.
Thank you.
Okay, okay, students, very good evening to all of you. I hope you are having a great Monday. So, yesterday already we have finished the thermal management, and also we have finished the CAN protocol. So obviously this type of things means thermal management, battery technology, CAN protocols. So these are actually very new to you also, as I know, because on my college days, obviously I also not aware about this type of things. Whenever I actually get into the industry, and obviously from the practical works, actually I got this type of concepts, that how to check the CAN IDs, obviously the how CAN protocol works, and how we are integrating all these things with each other. Supposed to be a charger, supposed to be a power electronics controller, inverters, battery management system. So obviously there is a huge scope for you guys also to explore this path. And today basically I will be starting the power electronics section. Means obviously you know that guys, in EV, especially in EV, as the name already stated, that uh, our 70 to 80% works on the power electronics. If I am talking about hybrid electric vehicles, then obviously there is a engine works. But in case of pure EVs, so there is a solely the electronics will means it will actually manage all over the EV performance. So for this, actually, you need to know about the importance of the power electronics. That in which components and where actually we are placing these things, and what are the key common components actually we are using in EVs. So especially for electrical electronics, EC guys, so it will be more beneficial for you also. Uh, that obviously I think that you already have your LinkedIn accounts, right? And I hope in which domain actually you belongs, supposed to be electronics, supposed to be electrical, supposed to be mechanical. So I hope you always follows your key manufacturer or key players in the industries. So obviously follow them on the LinkedIn, so that you can get the latest, we can say, the technology, right? Whatever they are working on, so it will be means for you, actually it will helps you a lot to know about the present means works actually going on in the industry. And we know that EV industry, aviation industry, so these two industries are means on the upper side, obviously. After that there is a consumer electronics and other things. So let me share my screen, just give me 1 minute. So I hope you can able to see my screen.
Yes, sir, it is visible.
Yeah, thank you. So what means, already we have taken so much sessions on the battery technology. Here also we have seen the BMS. So all of the working on basically electronics. So if I am talking about the hardware designing, if I am talking about the software modeling, So obviously there is a, in software modeling, obviously there is a role of CS embedded. But in case of hardware development, there are multiple things actually we are connecting with power electronics. So from the slides also you can understand that what are the things actually we are uh, means covering in the power electronics. So obviously in every segment, in every parts, so there is a power electronics. If you see the means this is a core branch, means core we can say subjects of electrical electronics, right? Analog, digital, electromagnetics, power system, control system, machines, circuit theory, signal processing, right? So these are the core components of power electronics. Now let's see that what are the major point actually we are using the power electronics. So on the right hand side actually you can see, this is a rough block diagram of the overall electronic segments. So here multiple auxiliary components actually I think you can observe that there is a auxiliary battery pack. You can see 40 volt 14 volt batteries, nearly 12 to 14 volts actually we are using. So in case of IC engine based vehicle also we have used this type of auxiliary battery packs. Now in case of EVs we also do use this type of auxiliary, means this is a low voltage battery packs. So whatever the EV batteries we have seen, so that are high voltage battery packs. So obviously there should be a DC to DC converters. So what does it mean, DC to DC converters? So already we know there is a DC system, right? Whatever the battery technology we have seen lithium ion, so obviously the battery technology depends on the DC power. So from that high voltage power, we have to step down that voltage to a 12 volt or 14 volt level for the auxiliary loads. So here basically auxiliary loads, you can see that the rear front blowers, water pumps, air fans. So this type of things actually works on auxiliary loads or auxiliary battery, we can say. Or maybe there are LEDs, indicators. So there are multiple other things are also there. So here basically we need a DC-DC converters to convert the high voltage battery pack from, means obviously we have to step down the voltage from supposed to be 300 to 12 volt or maybe 400 volt to 12 volt. So in this auxiliary system the voltage is fixed, that is 12 to 14 volt fixed. But in case of suppose depends on vehicle, actually we are designing the battery pack. Already we means I have shown you the case study, right? That which company actually using which type of battery pack and how much voltage it is. Means for Tesla, Mercedes, BMW, Tata, all of them actually are using different voltage, means their DC bus voltage are different. Now if we see in this market, at present market, so all the HEVs, hybrid electric vehicles, are plug-in type, right? Every vehicle having their own onboard charger, right? As well as offboard charger also. So for offboard charger, obviously they are dependent on a different manufacturer. So obviously they are not, means OEMs are not designing their own chargers. Yeah, even it is onboard or offboard. So they are basically dependent on the, there is a third party manufacturer, or we can say OEMs. So here also in onboard charger also we are designing two types of converter. One is obviously our overall ecosystem is actually working on AC, right? So we need a AC to DC converter. Now after converting the AC to DC, so we have to regulate those voltage on a battery pack voltage level, right? Suppose we are getting 230 volt AC in case of single phase, and in case of three phase obviously there is a 440 volt AC we are getting. In case of three phase supply management, obviously there would be a AC to DC converters. And in single phase also, suppose you are charging your vehicle with a offboard charger, suppose you are using our home supply. So on that case, obviously there would be the input voltage would be nearly around 230 volt. So depend on your input AC voltage, the overall function will be changed. So obviously there will be a three phase and single phase system would work separately. but our main goal is to charge our high voltage battery pack, right? Now in AC to DC, after that there is a DC to DC. So we will talk in the charger class session basically what are the internal block diagrams and other things. After that there is a traction inverter. So all we know that in the motor technology itself, we have seen that we are not actually using any kind of DC motors. Our all application will depends on AC motors. So obviously to control the AC motors, we need to convert the DC to AC, right? So that is the inverter operation. So that is why actually we are using a DC to AC converter also. So that is nothing but a controller itself. It means how actually we are controlling the speed of a supposed to be a PMSM, means permanent magnet synchronous motor, or it may be brushless DC motor, or maybe it may be induction motors, right? So all these type of AC motors can be controlled by these traction inverters only. So there are huge means powered traction inverters actually we are using, supposed to be 50 kilowatt, 70 kilowatt, 100 kilowatt inverters are also we are using. So obviously there is a huge scope in the inverter design itself. DC-DC means there are multiple separate companies are there who are only focused on the traction inverter designing. Also there is a multiple companies are there, they are focused on the DC to DC converter design. Especially I'm talking about this high voltage to 12 volt system DC-DC converter design. So just take any example, supposed to be Tata, Mahindra, or MG, Kia, whatever the top EV players are there. So they are not actually manufacturing or designing their own traction inverters, DC-DC converters or inverters, right? They are also importing these things, or maybe they have their vendors. So means as of my knowledge, I think there is a company in Chennai that is Valio. Valio also designing traction inverters for, I think they supplied to Mahindra maybe. I have heard about it because one of my friends actually in Valio, he's also designing this type of traction inverters team. Basically, in traction inverter team actually, he's working. So obviously there is a lot of scope in this industry. So now there is a okay. We already got right onboard charger, traction inverters, DC-DC converter. So these three are the major points, right? Where actually we are using a full-fledged power electronics, as well as obviously in the battery pack itself we already used BMS. So that has a different power electronics, right? So all of these type of designs, you should know about the basic of power electronics. So what are the key components actually we are using in this type of designs, right? Now, what are the basic components of power electronics? Means in every circuit, whatever the circuit you have seen means up to now, in every circuit, this type of components are very common, right? Capacitors, resistors, inductors, diodes, integrated ICs, transistors. So these type of components are very, very common in all of this circuit. Now, in power semiconductor devices, especially this type of devices are so much popular. MOSFETs, IGBTs. Nowadays, it is very, very popular. That is SiC and GaN, right? I hope you guys have heard on the charging segment. Means I am talking about the mobile charging segment. That is GaN based charger, right? High efficiency, and there is a very small charger which can actually give you a 100 watt 120 watt means output, right? So fast charging, everything fast charging is going on nowadays on SiC and GaN. So this is basically a transistor, means a part of a MOSFET we can say. So this is widely actually spreading and it is very much popular nowadays, SiC and GaN based design. So I am also working on that SiC based design. Basically, in my BLDC controller also, I have used SiC chip. So it is phenomenal. The performance is phenomenal. Uh, but obviously, this is a very new thing to us. So there is a lot of scope of improvement on this type of designs. SiC and GaN based I am talking about. And Obviously, there is IGBT in case of traction inverters. Whenever actually we are talking about high voltage system, so obviously our DC system is on high voltage, right? Most of the motors actually are working on 440 volt. Obviously, we actually controlling the voltage whenever actually we need to control the speed of the motor. So, but obviously the range would be on higher side. So obviously, whenever we are using IGBTs, actually SiC can easily replace those IGBTs, because most of the SiC technology is for, especially for 1000 volt MOSFETs, right? Nearly. In case of solar application, also these type of SiCs are taking a lot of advantage of nearly. I think they have developed nearly on 1.8 kilovolt rating SiC, right? Silicon carbide based MOSFET. So, okay, SiC means silicon carbide and GaN means gallium nitride. So these are the components actually we are changing on the MOSFET side. So that is how actually we are implementing the high frequency operations, high voltage operations. So there are multiple companies are there. I hope whoever in electrical electronics ECE domain, I hope you have heard these key names. Suppose like obviously there is a Texas Instrument, ST Microelectronics, ON Infineon. So these are the means top players in the industry, and I always recommend you to follow these type of companies. Means on LinkedIn actually I am talking about. So you will get recent solutions, and obviously on EV as well as on solar. So especially on EV domain, you can see actually there are multiple types of integrated chips actually they are working on, as well as they launched every month, in case of charging, in case of traction inverters, in case of supposed to be voltage sensing, current sensing, amplification. So there are a lot of ICs are there in their portfolio. So obviously from that actually you can get a very good idea. And also they have shared the design notes. Means you can simply download the design notes, and every calculation formula, in-depth analysis, everything they have written on the design notes. So from the design notes itself actually you can get the waveforms that supposed to how to select the every components, right? So that type of features actually they are providing. So today also I will show you some key notes or key design notes on basically on onboard charger, right? So the onboard charger market is very big. Onboard and offboard charger, basically in charging segment there is a huge market, guys. So there is a very good scope for you also uh, to get into this EV ecosystem. So in case of passive components, there are a very important component, that is transformers. So already I think you are everyone, each of you are actually familiar with transformer, right? So where you have seen the transformers rather than any kind of circuit, where you have seen the transformers, and it is very common, right? In our power transmission line. So it is very common this type of transformers. But why we are not using that type of bulky bigger transformers? So there is also a concern, right? So in EV, we are using 100 kilowatt systems, right? 100 kilowatt, 60 kilowatt, 90 kilowatt systems, right? But we are not using that type of big transformer inside it, right? So there is a concept behind this. So that is why means magnetics design, inductors, transformers is actually a magnets, right? Magnetics design. So in magnetics design also there is a lot of scope. So means magnetic design is a very important part of this type of converter design. If I am talking about DC-DC converters or inverters, right, or charger design, so magnetics is a very key component. And after that, there is a capacitor, resistors, diodes. So already you know, guys, these basic things. So how actually it works, in which circuits we are using. So after that, there is a control units, obviously MCU, DSP, means real time control. Whatever the we are controlling all the things actually, that is a real time control. All of this type of applications are on microcontroller based applications. So obviously there should be real time control, and there is some PWM IC. So what does it mean, PWM? So that is nothing but a pulse width modulation. Means whenever suppose we want to control a voltage, right? I want to step down a voltage from a 400 volt to 212 volt. So I want to control the voltage, right? So obviously that would actually depends on the PWM, pulse width modulation techniques. So there is a lot of techniques. Actually, I am not going into deeper on this. How every obviously I will show you some data. Now there is some information on transformer works, that how actually transformer works. So these are the basic things actually you should know. Already who have done their machine classes, so already they know about it, I think. Because in machines actually we are starting with transformers, right? So after that we goes to induction motor, after that there is a DC motor, after that there is a synchronous motor. So synchronous motor is the upper one, right? So we are starting with transformer. So this is very easy, obviously. That is nothing but it will work on electromagnetic induction. So right, for isolation purposes, widely we are using this type of topology. In EV especially I'm talking about. In consumer electronics, actually we used multiple other topologies. Buck converter, boost converter. So means non-isolated converters. Means there is no isolation between the input side and the output side, right? So two types of designs actually we follows in industry. One is a isolated design, one is a non-isolated design. So obviously non-isolated design actually having a pretty drawbacks in case of supposed to be control algorithms, in case of supposed to be power management, also in case of safety also. So that is why actually now we are pretty much focused on the non-isolated design. Now in case of power circuits, in case of signal circuits also, we are using isolated designs. So for power isolations, we are widely using this type of transformers. Now, whatever the transformers actually we are using in this kind of distribution system, right? So that are basically which type of transformer actually we are using. Any idea, guys? Which type of transformer? Basically core type transformer we are using, right? In this kind of distribution system, very bulky transformers, right? But in EVs, not only in EVs, basically for commercial applications, or we can say uh, as we are pretty much advancing our EV technology, so in EV, in aviation, so we are actually using ferrite core transformers. So means how actually this depends, why actually we are choosing ferrite cores. So basically to reduce the size of a transformer, actually we are choosing ferrite cores. So whenever actually we are actually increasing the frequency of a transformer, as you know, normal AC means whatever the distribution systems actually works on 230 volt or 440 volt AC and 50 hertz, right? There is a frequency of 50 hertz actually we are using, and that is in India basically we used 50 hertz, and in US we use 60 hertz, right? 120 volt 60 hertz operation, and in India we use generally 230 volt 50 hertz operation. So whenever actually we are using a 50 hertz operation, or we can say there is a high frequency switching actually we are doing. Whenever suppose we are designing a DC-DC converters, I will show you some data, because means there is a lot of data in it, means inside this power electronics. So means it needs that if you want to cover the power electronics, obviously if you need to know all the things in depth. But I am talking about on the overview means segment basically. So in case of uh, whenever we are designing a DC-DC converters, or suppose like a inverters, on that case actually we are doing high frequency switching. So this type of mechanical switches, whatever the switches actually we are using in supposed to be home, obviously that are the mechanical type of switches. The electronic switches basically we are using, that is the MOSFETs, IGBT, transistors, BJTs. So this type of switches, electronic switches actually we are using, and that can be controlled via microcontroller unit. So that may be voltage controlled, or that may be current controlled, right? So whenever we are designing DC-DC operations, on that case actually we are doing high frequency switching. So what does it mean, high frequency switching? Means rapid turn on, rapid turn off. Means supposed to be the frequency would be like 100 kilohertz. So means you can understand that how much frequent turn on and turn off we are doing, right? So that is the main purpose, to reduce the size of a DC-DC converters, inverters, right? So whenever we are doing a high frequency operation in case of transformers, so the core area actually is reduced. So that is why actually we are choosing this type of high frequency operations. So our in this design, to be practical, why I am also using SiC in my design. See guys, to be very practical, I use whenever actually I have started with VLDC controller design, I have started with a 20 to 30 kilohertz design, right? After that, I gone to 50 kilohertz design. But that type of 50 kilohertz design actually needs a bulkier transformer. Obviously, that are very small rather than the other type of transformers. That is a ferrite magnet actually we are using. But whenever actually we used SiC and GaN based solution, which is basically working on supposed to be more than 100 kilohertz. So on that case, we actually reduce the size of the controller. So this is a very good advantage actually we are getting whenever we are rising the switching frequency. But whenever we are rising the switching frequency, we have to keep in mind 2 to 3 things. Obviously, the magnetic design means obviously depend on the frequency actually. We have to design the number of turns, wire gauge. So I will show you my design means in my whenever actually I have started my career. So on that time actually I have designed a DC induction cooktop. Whatever the induction cooktop we are actually working on AC. So I have designed a DC induction cooktop. So that is very easy. Uh, means there is only a integration part and DC conversion part will be there. So I will show you that design obviously. So that was also I have worked on 20 kilohertz operation. So depending on the frequency, everything will be changed. Your core selection means your transformer size, your number of turns, as well as whatever the wire gauge actually you are selecting. So our main purpose to design a transformer is for step up or step down the voltage, right? In case of distribution system also, whatever the in generating station, in generating station basically we are generating 11 kilovolt. 11 kilovolt systems actually we are generating. After that, we are just step up this voltage up to means 400 kV, 440 kV. After that, there is a 132 kV, 66 kV. So there is a lot of transmission grids are available in India, right? So after that, at the end, we can say consumer, we are using 230 volt, right? So there is a every step up, step down operations actually going on basically on by transformer, right? So in this transformer operations, we can say the power is absolutely constant in the primary side as well as in the secondary side. If we are stepping up the voltage, obviously the current will be lower, right? The power is constant. So yes, obviously there is a loss. So yes, so regarding the loss also, why actually we are using high frequency operations in this kind of ferrite magnet based transformer? Actually the efficiency of this type of transformer is nearly around 95%, right? And those core type transformer, which transformer actually we are using in distribution system, that type of transformers actually having nearly 80% efficiency, 80 to 85, maximum 85%, if you do proper cooling and this arrangement. But most of the time actually we ended up to 84 to 85% only. But in case of ferrite magnet based transformer technology, actually we can get up to 95 to 96% efficiency. So you can get that 10% is huge. So in EV industry, we have talked on motor technology, right? We rejected DC technology, means DC motor technology, right? On that case, obviously we are actually getting a more 5 to 10% more efficiency on AC motor. Now if we can get a 95% efficiency on our traction inverters or whatever the conversion techniques actually we are using, so obviously it will be beneficial for us. We can get more 10% range, right? So that is why also we are using this type of high frequency transformers. Now, obviously there is a, I am not going into deeper that how transformer basically how EMF actually induced, how flux is flowing through primary to secondary, right? There is a, but yes, one thing you have to keep in mind that whenever actually you are designing a transformer, so obviously you have to follow the frequency as well as magnetization curves, and also there is a primary secondary turns ratios, right? Also there is a ferrite core, the magnetic property selection, right? There is a different kind of materials actually we are using in ferrite magnet also, right? So there is a magnetic course actually we are using, so that is why actually we are increasing the efficiency up to 95%. And also you have to keep in mind that depending on the design construction, right, means depending on the wire gauge, depending on the we can say the process, right, how we are actually applying the turns. After that, suppose it's in the single layer winding, double layer winding, or there is a how much number of parallel wires actually we are using. So depending on that, a lot of things actually changed, right? Regarding efficiency also, means there is a gap of nearly 5%, right? Means you can also improve up to 5% depending on your magnetic design. Suppose you are using same magnet, right? Two same magnets actually you are using, but depending on your design considerations, a magnet can give you 95% or 92% efficiency, and B magnet can give you 96% efficiency, right? So obviously same magnet you are using for same power application, but yes, obviously this type of things actually matter. So I have also experienced a lot of things, lot of R&D actually is going on magnets on a daily basis, right? So that is why I'm talking about magnetic design also. It is a means very good thing actually. You can start also, means in this kind of DC-DC converter, yeah, inverter designs also. The company is actually looking for a good magnetic designer, right? So obviously for that you need a in-depth knowledge on the core materials or this kind of things, right? So now obviously transistor, that is also a very key components are there in the BMS also. We have seen that on the block diagram itself, that we are widely used MOSFETs. Now there is a, means it is a key component. Whatever the component already we have discussed, that is transformer, that is also a key component. And it is, means the transformer is actually connected with the MOSFETs. Whatever the conversion we are doing, DC to DC, DC to AC, everywhere actually we are using MOSFET or IGBTs, right? Whatever the SiC GaN I am talking about, that is nothing but a power semiconductor switch, right? Whatever the switching applications we needed, for that obviously we need a switch, MOSFETs, BJTs. Mostly we use MOSFET and IGBTs. So BJTs we are rarely use in the signal path. Basically on the power path, always we use MOSFETs. So from the BMS architecture also you have seen that on power path controlling, so we are using MOSFETs. Now there is a two types of MOSFETs are widely we are using. One is N-channel MOSFET and another one is P-channel MOSFET. So it is very common to industry, NMOS, NMOS, PMOS, NMOS, right? So depending on your application, means there is a switching techniques actually are there. Means high side switching, low side switching. So I am not going into very depth on this high side switching, low side switching, but yes, uh, just for your information, in case of obviously high side switching, we use PMOS, and in case of low side switching, actually we are using NMOS. Now in MOSFET, actually there is a three terminal. So now you may have questioned that in mechanical switch, that is controlled by our hand, right? So how is this MOSFET, means this electronic switch actually controlled? So obviously it needs a voltage pulse or maybe a current pulse, right? So MOSFET is basically a voltage control device. Means you can see there is a three terminal, right, on the block diagram, that is drain, source and gate. So gate is a controlling parameter. So we need to give a pulse pulse maybe obviously depend on your MOSFET data sheet. So I will be showing you a data sheet as well, that how actually you should select a MOSFET also. So that is also very crucial point, especially in power electronics. So in case of MOSFET controlling, we need to give a pulse in the gate. Suppose we want to turn on a MOSFET. So obviously we have to give a voltage pulse in the gate. For NMOS, the pulse should be positive. For PMOS, the pulse should be negative, right? So that is the PNP thing actually. So obviously that means the drain to source terminals, normally it is in open circuit condition, in normal. Suppose there is no gate pulse actually we are giving. Suppose there is an open circuit gate. So obviously your drain to source, these terminals are in open circuit condition. Whenever we are supposed to applying a voltage in the gate terminal, it may be positive, it may be negative, depends on your N channel or P channel. So this drain to source point will be short circuited, right? And obviously in automotive segment, see, whenever actually the manufacturer designed MOSFET or SiC, so they also conclude two things. So same MOSFET, this is for automotive grade and another one is for industrial grade. Means they designed two different MOSFET with same part number, same rating, but for automotive grade, obviously there is an advantage, irrespective of the other grades. Means obviously there is an industrial grade only. And in the top of the thing, actually we used aviation grade, right? So mostly in automotive grade, we have to select automotive MOSFETs basically. So obviously in MOSFET means whenever suppose you are starting your career, right? As a hardware designer, I am talking about. Suppose as a hardware designer, you are starting your career. Your first 6 months will be on component selection, right? Means how to select a component according to your application. Suppose you are designing a onboard charger, right? Supposed to be 3 kilowatt, 4 kilowatt, 7 kilowatt charger. You are supposed to design. Means not you are designing. These type of big projects actually require a team, right? There is a 20 to 30 people are designing on a means designing, right, for a project. So obviously whenever you will be starting a career, obviously there will be your role will be of the part selections, means depending on your application, right? So obviously there is a means in case of MOSFET, in case of IGBT, in case of BJTs also, transistors also, actually we are using for only switching applications only. And after that there is the integrated circuit. So the integrated circuits actually means this is a C, right? Means there is a multiple types of components are there. So means you can a small integrated circuit, by using a small integrated circuit, resistance, capacitance and transformer, actually you can design an inverter, right? Means I am talking about a hardware based inverter, right? You can easily design this type of inverters, right? Means that is not a big deal. uh, means in the industry also you have seen the square wave inverters, right? But that type of square wave inverters actually we are not using in case of EVs. So in EV, all the traction inverters are purely sinusoidal and obviously controlled by microcontroller itself. So integrated circuits, it is nothing but a powerhouse, right? And the BMS also, in the BMS architecture, I have shown you a AFE, right? Analog front end. So what actually that AFE is? So that is basically a voltage sensors, right? That is actually sensing the temperature, sensing the current, obviously in the form of voltage only, but it is actually controlling all the data and it is sending those data to the microcontroller itself, right? So this is in case of BMS, you can think about this. There's a heart and brain, right? So obviously uh, means integrated ICs are very important for your operations. Whatever the pulse width actually we are supposed to use, right? Obviously there is a microcontroller microprocessor based we can do, right? But inside the microcontroller, inside the microprocessor, this is also integrated IC, right? Nothing more than that. So whatever the Arduino we are using, whatever the Raspberry Pi you are using, whatever the STM32 you are using, so everything is a integrated IC. Whatever the pulse, sensing, conversion, mathematical operations, suppose to that clock we are using, everything actually are integrated ICs. So nowadays in EVs also we are using means IoT systems, right? Geofencing. So everything actually depends on integrated ICs. So there is a particular ICs actually the key players have developed. Suppose for CAN IC, already I told you that for CAN communication there is a separate CAN IC actually we are using. So from CAN high to low, it is converting all this data to a 0 1 level, and it will be sending to the microcontroller. And after that, the microcontroller processing, it will means obviously give the feedback to the CAN controller. Obviously, same as we are getting these IDs, right? Whatever the IDs actually we have seen yesterday, that CAN IDs 15A, 16A, whatever the codings actually we are doing on inside this. So everything will be depends on this integrated ICs, right? And in these integrated ICs, there are billions of transistors, billions of diodes, resistance, capacitor, everything is we are using inside this small chip, right? So, uh, since I don't know, is there any master student from VLSI especially? So in VLSI technology, actually, you can get a very good in-depth analysis on this type of integrated IC. How actually we are doing the layouting, right? How copper foil actually we are using, right? How we are actually designing this type of very small chips with billions of transistors. So especially in masters or PhD, there is a in VLSI domain actually there is a lot of scope also is there also in chip manufacturing industry. So after that diode, it is also very common component actually we are using. Uh, means here basically in the circuits actually this is a DC means it AC to DC circuit, right? You can see there is a 220 volt, and after that we are getting a 12-volt system. Inside this you can see there is a transformer, there is a key component I have told, and there is a switch, that is MOSFET, that is also a key component. So these two key components already you have seen, right? And after that there is a diodes, and obviously all the things, right, all the controlling segments actually controlled by a controller. So this is basically a hardware based model. So here basically we use the BJT, then op amps. For digital isolations actually we use op amps. So but yes, our main purpose is that for diode actually we are using for rectification. So there is 3 to 4 types of diodes actually we are using in industry. One is for rectification purposes. One is for that is a Zener diode. So that is for regulating the voltage. That is also a purpose. Also, there is a TVS diode we are also using. So TVS diode is we used for safety purposes, right? And there is a fast recovery diodes also we are using for rectification. Very good. In this case, this 220 volt, there is the frequency is nothing but around 50 hertz. And in the output side, after high frequency switching, there we have to use a high frequency diode. So depending on frequency, there is a variation in diodes, right? Uh, for diode selection also, you have to look into in detail, right? The voltage drop across the diode means whenever suppose I am designing a ELDC controller. So on that case also I have to means remember on that how much voltage drop that I have to select for diode. So obviously if there is a high voltage drop, there will be high losses, right? And also nowadays there is a new technology that we are using, that is synchronous rectification. So whatever the normal diode rectification we are doing, that actually replaced by a MOSFET based control, MOSFET based diode control technique, right? Means rectification technique, sorry. So in each of the component, there is a means in depth means there is a concepts in MOSFETs, in transformers, in diodes, in power semiconductor ICs, right? And the very common things that we are using resistors and capacitors. In everywhere, actually, we are using resistors and capacitors. Suppose we want to okay, diode. LED also a type of diode, right? Light emitting diode, which is widely used in industry nowadays. So obviously, in home applications, there is a LEDs actually we are using nowadays. That is also a diode, right? So we are There's everything actually dependent on electronics, we can say, right? Now resistor capacitor is a very basic components. Everywhere actually we are using this kind of resistors and capacitors for voltage division, for current limiting, for obviously mainly these two three purposes actually we are using, from reducing the voltage spikes, right? And another things also we used supposed to be capacitors. So there are multiple types of capacitors also we are using to basically control the voltage, means basically to constant the voltages. So there is a two three type of capacitors we are using. So electrolyte capacitors, ceramic capacitors. So there is a in-depth analysis on capacitors itself, how to select those things. Means there is a ESR, equivalent series resistance, in the capacitor. So there is a lot of things on that also. Now what are the important concept for beginners, right? There is a switching, means I have written here losses, means whatever the, suppose you are designing a charger. So obviously you have to keep in mind whenever you are supposed to choose a MOSFET on that, you should actually have the switching conduction losses, right? You should have calculated pulse width modulation. In case of DC-DC converters, whatever we are using for auxiliary, uh, means transformation, right? Auxiliary, whenever we require to design auxiliary DC-DC converters. So on that case, pulse width modulation you need. Sine PWM technique, it is basically widely used in inverter technology. So in traction inverters also we use SPWM, means sine PWM technique. Uh, so obviously you have to keep in mind this PWM, means pulse width modulation techniques, right? And there is in thermal management, obviously there is a thermal management is there. In case of PCB designing, it can control your thermal, right? Whatever the big inverters actually you are using, right? 100 kilowatt inverter. So you have selected all the things perfectly, right? Transformers, switches, integrated ICs, resistance, capacitors, everything. But you are designing a poor PCB, right? PCB layouting is poor. So obviously that will be given you a very high thermal. Means that means this it will be actually heated up. So on that case, actually there is a very good point for a means how actually you can uh, design a proper PCB layouting. Right? That is also a dependency. Heat sink selection for MOSFETs, we are using actually heat sinks to basically extract the heat from the MOSFETs. So force air cooling also we are using in case of inverters, converters, chargers. Actually, we are using. So basically, this type of cooling systems you have to focus on. EMI, EMC filtering. This is also a very vast concept. EMI, EMC. In EV especially, suppose whenever actually we are supposed to going for certification, right, for battery pack certification, on that case we have to submit our EMI EMC certification for BMS, battery management system, right? I'm talking about only battery pack manufacturer. For traction inverter manufacturer, they also have to be passed from EMI EMC, right? So this type of things also you have to keep in mind. So there is a lot of arrangement we are using in case of PCB designing also, in case of high frequency operations also. We are using filters, right? Basically overcome these EMI EMC problems. I think you may have some here, since you have experienced that in LED, whatever the LED actually we are using nowadays in home appliances. On that case, whenever suppose you are turning on a switch, I have experienced those things. Basically, in every 5 seconds, 10 seconds, there is a noise from the LED itself. Actually, we are getting. Now, what is that noise? What type of noise actually it is? That is a magnetic noise, right? Transformer noise. So that is basically developed for EMI EMC, by EMI EMC basically. So that type of things, whenever actually you are in you are a designer, right? So on that case you have to keep in mind these things. And also the last one, that is the isolation. So isolation is very important for your system. You can see that on the circuit here also, the power isolation actually done by the transformer. You can see the primary secondary actually is not connected. For digital means for signal isolations, actually we are using a optocoupler, LED based opto model, right? That is also a very good components actually we are using in every circuits, right? Digital basically it is named as optocoupler. So depending on the signal actually we are getting on the output side, that is LED side, our transistor is turned on the primary side. So that is how actually we are controlling the signals. So that is why actually we needed power isolation as well as signal isolation. So whenever actually you are designing this type of converters, right, or controllers, so this kind of information or this kind of design practice actually help you to design a reliable solution, right? You obviously don't want that you design the inverter and after 2 months, 3 months, there is an issue actually we are getting. Obviously, in case of EV, we can't be means we can't imagine this type of errors, right? There is a speed control techniques. All of these things actually depends on this, right? So that is why actually for a perfect designer, obviously we have to follow the design rules. So that is the importance of power electronics. Means these type of components you should know about, and actually I want to share with you. One second. Okay, we can take a 5 minutes break, right? We can take up from now 5 minutes break, right? No, actually, I am not speaking anything. I just given a 5 minutes break, and already 3 minutes gone. Means just uh, after 2 minutes, actually, we will be starting the charging technology. So before actually starting with charging technology, that is why actually I have actually given a small brief on power electronics to you guys, because before entering into the charging technology, obviously there is a algorithm behind the lithium ion charging. Also, there is a hardware management. So obviously, as as a power electronics enthusiasts, right? I also just want to share with you such kind of designs that you can follow, because you also want to design a charger, you also supposed to design a battery packs, you suppose you want to design a BMS, so in final year projects or in third year, fourth year, any. So obviously you should enter with these things. Obviously you should follow the design notes, whatever the TIs on semi. There are multiple players are there. But yes, obviously for your knowledge, you can absolutely start with this type of top manufacturer. But to be very frank, whenever actually we are in an industry, on that case, there is a lot of Chinese solutions are there, because you have to meet the cost as well, right? So yes, we use, but suppose there is a 10 ICs actually we are using, 10 integrated ICs we are using in supposed to be in inverter, right? On that case, we use 2 to 3 top players, but rest of the parts actually we choose Chinese one. Why? Because of cost to quality complexity. So in the actual market, actually, we have to very much dependent on the cost also. There is a cost centric market. If you see for the two wheelers, even if four wheelers also, right? So yes, obviously there is a reliability in the top players rather than using a Chinese one. But yes, depending on your warranty period, depending on your applications, actually, you have to choose those ICs, especially. Now, uh, we will be starting with the charging technology. For that, before that, actually, we have seen one topology, or we can say one, uh, basically one word actually we have also here, that is CCCV technology. So what does it means? What is CCCV technology? So in, I think on the BMS classes, actually I have stated also, that is constant current, constant voltage charging. So whenever actually we are, in case of normal chargers also, even if it is a phone charger, then also we are using CCCV charging, right? So already I told you there is a SiC based, GaN based solution actually we are using. In case of EV chargers also, we are using GaN based or SiC based charging nowadays. So that actually we can actually reducing the size, right? We need a very small transformer, we need a very small components, mainly the weight and the overall uh, size actually depends on the transformers. So whenever actually we are doing high frequency operations, we are actually reducing the transformer size. As a result, obviously we are reducing the weight as well as the uh, uh, means weight as well as the area, right? The size. So what is the lithium battery charging profile? So in the data sheet, whenever actually we have started with the data sheet, right? There is a NMC and LFP data sheet we have seen. So everywhere actually they written one thing, that is a C rating, right? 0.5 C, 0.2 C maximum charge, 0.3 C maximum charge. Now depending on that 0.2 C, 0.5 C, actually, obviously we will calculate the current. Suppose we are using a 2 mAh cell, right? And we are using 2 mAh cell, 10 cells in parallel. Please be noted, 2 mAh, sorry, 2 AH cell, 2 ampere hour cell, 10 cells connected in parallel. That means the overall capacity is nearly around 20 ampere hour, right? 20 ampere hour. Now I want to design a charger for this battery pack, right? I want to design a charger. For this 20 ampere hour, in each cell they have written it will be maximum charged up to 0.5 C. So what does it mean 0.5 C? That means for a 2 ampere hour cell, 1 ampere will be your maximum charging current, right? For each cell. That means 10 cells is connected in parallel, right? So obviously we can apply up to 10 ampere of current, and we can charge this 10 parallel cells, right? Each of 1 ampere. Now we have to design a 10 ampere charger, right? So whatever the CCCV technology we are talking about, that is CC, that is constant current. That means the maximum current actually we required. So the 10 ampere, this 10 ampere range is nothing but that constant current range, right? Obviously we have to regulate the current as well as we have to regulate the output voltage also. Now a case scenario. Whenever suppose you are charging a battery pack, actually you only I think have familiar with the mobile phone batteries, right? Now if suppose you want to explore more in the charging, just uh, means from your charger, means you can do some R&D, right, on that. So from the charger actually you will get a 4.2 volt output. If you suppose to cut the wire, and obviously from positive negative you can actually get the 4.2 volt. And suppose whenever your battery is nearly around suppose 0% charge or 5% charge, so how much would be your battery voltage? Mobile phone battery I'm talking about. Obviously you are using a NMC, right? Mobile phone we are using NMC. So in case of NMC actually the voltage would be for 5% in nearly around 3.2 volt, 3.2 to 3.3 volt. On that voltage range actually we were getting that 5% state of charge. Now whenever suppose we are connecting the charger, on that immediate moment obviously your charger voltage, whatever the charger voltage we are getting in the DC bus, right, on the output we can say 4.2 volt, it will reduced whenever suppose we are connecting the charger with the battery, right? Two wires connected and we turn on the charger. On that point if you put your multimeter, you will only see the battery voltage. Means you are applying 4.2 volt and you can see the battery voltage 3.2 volt, right? So on this state actually named as a CC state, if you can measure the current, then you will be clarified actually the charger will push on that time a constant current, right? So first actually we are starting with constant current. Here basically I have taken two more example, that is trickle charge and the pre-charge. That is specially depend on the EV charger, not in the phone charger, cell phone charger. Now let's started with that one first, trickle charge and pre-charge. We know that uh, most of the time, see, cell phone we are using on daily basis, right? Suppose you are not using your EV from 10 days or 15 days and your charge is depleted, right? Suppose 0% means you coming back from office or anywhere you're coming back from there, and due to any reason suppose you unable to charge your EV and you left your EV for at 0% for supposed to be 10 days or 14 days. So obviously there is a BMS in the battery pack. It has a consumption, right? And suppose you are not charging your battery pack for maybe minimum 15 days or maybe 1 month, right? So your initial consumptions, see, most of the time actually it doesn't happens because the BMS also having a sleep mode mechanism. On that sleep mode mechanism, after means suppose there is nothing we are using, right? There is a no more activities actually we are doing. On that case the BMS after suppose 24 hours actually it will goes under the sleep mode. So on sleep mode there is a microampere consumption, means there is a very less consumption, right? But there is other systems are also activated on that time, right? There is a BMS obviously activated. On that case IoT system also activated, right? Sometimes we are actually we need a supply to actually for powering up the IoT system, right? That needs a separate hardware. So on that case sometimes I have also have seen this type of phenomena. Means I have designed a battery pack for Battery Smart. That is a company named Battery Smart. That is also swappable player. So we have used the IoT system, IoT module for that, and basically that IoT system is directly connected to the battery pack, right? So there is a very less consumption in the BMS, but there is a consumptions also in the IoT module itself. So there is a chance of deep discharge of the battery pack. Means suppose any of the player actually, suppose any of the customer, they have discharging the battery 0% and they put the battery pack in the suppose charging stations. And I have seen those battery smart charging stations. There is a, I think, 100 to 200 number of battery pack is charged at a time, right? 200 250 batteries are charging at a time. So there is a, means a lot of battery packs actually they are placing here and there, right? So on that same time actually we have seen that some battery packs actually have not charged for 1 week, 10 days, 15 days also. So that is the main concern. But in case of, obviously in case of EVs, that is the means we obviously at least we plug in our charger at least once a week, right? But yes, there is a possibility. I'm talking about there is a possibility to deep discharge for the battery pack. What is this deep discharge? Mean whatever the 0% SOC voltage we are having. Suppose for NMC model 2.8 is the lower voltage. Suppose you are not charging your vehicle and it drops up to maybe 2 volt, right? Or it may be 0 volt itself. It may be supposed to be 0 volt or 1 volt. Now you want to charge your battery back. So obviously 0 volt means you can actually get that, oh my god, my battery is damaged, right? 0 volt, that means nearly damaged position. But yes, suppose there is a 1 volt. I am talking about each cell voltage, right? Suppose we are getting a 1 volt. So on that case, whenever actually you are connecting your charger, first it will communicate with the BMS. BMS will sleep on the sleep mode, right, for many days. So whenever there is a connection, there is a power connection as well as there is a signal connection via CAN, right? Whenever suppose we are connecting a off-board charger or maybe on-board charger, so the connection establishment happen. On that immediate case, actually the BMS is sending some CAN data to the charger, and charger starts, obviously it sends the data and it's charged the trickle charging mode. So what actually we are doing on this trickle charging mode? In a duration of time, right? Suppose we are starting from now, after 30 seconds we are giving a 10 ampere pulse current and we will push for 5 seconds. After that we will stop. After 30 seconds, then again we will start and give a pulse for 10 seconds. See why actually we are giving this. Whenever a battery pack, a lithium ion battery, is in deep discharge condition, suppose below its operating voltage. For NMC, there is an operating voltage. What is the operating voltage? That is from 2.6 to 4.2, right? Nearly 2.6 or 2.8 to 4.2. Suppose the voltage is nearly 2 volt. So that is not under operating voltage, right? So that will be going into a deep discharge condition. So on that case, if you apply your full charge current, right, on that immediate case, what happens actually? That will develop a stress inside the lithium ions, right? So obviously, it can be short circuited. Obviously, it can damage your electrolyte, sorry, your separator, right? It can damage your separator on that case. And obviously, whenever we are using this type of deep discharge charging, right, very low voltage charging, I mean, whenever your battery is in exactly in discharging state, on that case actually the ACI layer development actually it is increasing, right? So that is why actually we are pushing a small amount of current for a small amount of time. So that is comes under trickle charge condition. You can see that here up to 2 volt, you can see we are actually applying a trickle charge. After that there is a pre-charge phase. So pre-charge phase means from that 2 volt condition to a nominal voltage. Not a nominal means a minimum voltage. The minimum operating voltage for NMC it is nearly around 2.8 volt or 3 volt. For LFP it is 2.5 to 2.6 volt, right? So we will be going into a pre-charge phase. So that will be also controlled by your charger, right? everything you have to written on the code. Obviously you have to run this algorithm inside your charger, and each data actually you are getting via CAN from the BMS, right? Battery management system. Each data, temperature data, voltage data, current data, right? Every data actually you are getting. Now sensing this voltage, I am talking about each cell data actually you are getting, not only the pack data. Whatever the data the BMS is actually having, every NTC data, every cell data, pack data, right? Current data, everything, every data actually it will be sending. Now, after 2 volt, you can see that there is a pre-charge. So typically, whatever the charger rating is there, suppose the charger is rated as 20 ampere. The the pre-charge current would be selected on your charging current, means that would be nearly around C by 10, right? Whatever the C rating we are using, suppose our charging current should be 0.5 C, right? 0.5 C, we are using a 10 ampere charger, right? Depending on 0.5 C, 10 ampere charger actually we are selecting. Now in this 10 ampere charger, we will apply C by 10. That means 10 by 10, that is 1 ampere. That will be your pre-charge current from this whatever the voltage we are selecting up to the minimum operating voltage. So that will be solely depend on the manufacturer, right? But obviously depending on your lithium ion battery profiling, whenever actually we are doing the profiling of that cell, right? For a better design, you have to do this type of testing, mean deep discharge testing, and after doing deep discharge, you have to give this type of charge mechanism, right? Trickle charge, pre-charge, how actually cell react. Is it overheated or not? Is there any so much electrical stress is developed inside the battery pack or cell I am talking about? So you have to do this type of testing. After that, you have to modify your algorithm according to your cell action, right? So this type of trickle charge and pre-charge is very very important. Is in on off-board charger as well as on-board charger, right? So this type of pre-charge mechanism should be there. Otherwise, means your charger will not get a certificate, guys. Whatever the EIS actually we are having, that should be a microcontroller based charger, communication based charger, and this should have a pre-charge mechanism, right? That is a very important factor actually for a charger design, right? So these two are very much important. Maybe trickle charge are not be there, but pre-charge should be there, right? After that, whenever actually we are suppose in a window of minimum operating to maximum operating window, on that case we are actually starting a constant current charging. You can see that from the graph itself actually you can get, obviously you can understand that this current, whatever the current here, that is 2 ampere, suppose like that is, yes, 2 ampere, from 128 milliampere to 2 ampere, right? You can take it. That is 100 milliampere, that is trickle charge current. After that, there is supposed to be 200 milliampere, that is a pre-charge current. After that, you can see that there is a sudden jump in the current. So obviously whenever actually we are on CC state, right, constant current state, so you will actually draw the maximum amount of current from the charger, whatever the charger rating is. Suppose it would be 10 ampere charger. So obviously it will runs on the 10 ampere charger. So whatever the fast charging mechanism actually we are doing nowadays, that fast charging mechanism, that means 30% to 80% actually it will works on constant current state. Whatever the 0 to 90, 10 to 90, it depends on every manufacturer. Most of the time actually we recommend to charge your battery pack from 20% to 80% in the fast charging mode. So this fast charging mode actually doing a constant current charging. And obviously we know that whenever we are connecting, what is the purpose of charger? To basically charge the battery voltage, right? So the battery voltage is gradually increasing. You can see that from trickle charge it will be increasing a little bit. In pre-charge there is a little bit increment. In constant current charge, or we can say this is a fast charge, on that state there is a huge increment, right, on the voltage increment up to 4.2. Suppose we have selected a 4.2 volt maximum voltage, right? See, in CAN communication, guys, the BMS also sending the cutoff voltage as well. In CAN communication means BMS is sending that in our BMS in this battery pack we are having a 4.2 volt cutoff. So depending on that 4.2 volt, the charger will cut off on 4.2 volt. Suppose BMS is sending 4.3 volt, the charger will act on 4.3 volt. The charger output voltage is varies, means there is a range, right? Suppose there is a charger we are designing for 60 volt, there is a range of operation from 50 to 70 volt, right? Depending on the BMS actions, the charger will change its output voltage. Means obviously in the cell phone charger you have not seen this type of things, but in EV charger this happens. Means everything is actually depend on your communication system, right? Whatever the BMS is sending, charger will act on that basis. Okay, so on that regulation voltage means after up to 4.2 volt it will be on constant current charge, right? Now there is a one more concern, why we need CV charging, right? You can see that at this CV mode, after CC there is a CV mode, right? The voltage is constant, the current is decaying, right? What does it mean? See guys, in everything already we know that every cells having their internal resistance, right? Every cells having their internal resistance. Now whenever actually we are supposed to charge, depending on that current there will be a drop. I think you guys agree, right? Suppose the resistance of the battery pack, means I am talking about the IR, internal resistance of the battery pack, is supposed to be 100 milliohm. Obviously that is very less, 100 milliohm. But suppose you are doing a 50 ampere charging, so on that depending on that 50 ampere charging there is some drop inside it, inside the cells. That means obviously to decrease that voltage drop, we are actually applying CV mode. We are not cutting off the charging whenever suppose we are sensing 4.2 volt reach. The 4.2 volt reach is it on the terminal only, not inside the cell, right? It is a very means important concept guys. Means why actually we need CV charging. On the CC whenever we have sensed that the voltage reached, immediately we can cut off. Why we are doing this? In cell phone also there is a CV mode, right? CV mode is everywhere, every lithium and battery pack charger having CV charging. You can take any example, cell phone charging, your trimmer, your any kind of remote controller, or you can take EV also, right? Now whenever we are decreasing the current, this CV voltage is nothing but on the terminal, not inside the cells. Now whenever this CV happen, this current is automatically decaying, right? This will automatically decay. You don't need to control anything. The current will automatically decay. You have to sense those current. You can see this current is decaying and your battery is slowly charged. That is why everyone have, I think, observed that after 90% of the cell phone charging also there is a slow charging, right? From means 10 to 90% it is a rapid charging. Within half an hour it is 10 to 90%, but from 90% to 100% it takes more time, even uh, more than half an hour, right? So this is under CV mode. CV mode, what happens, the current is slowly decaying. As a result, the drop between the terminal voltage and the inside the cell, that is also decaying. So obviously IR drop is directly dependent on the current, right? Current will be decreasing. As a result, your IR drop will be decreasing. So that is why we are applying CV voltage. Now you have to take a action on charge termination. There should be also a cutoff, right? So depending on the manufacturer, means cell manufacturer, there is a thumb rule, guys. Every time we select nearly around 0.01 C, right? Means sorry, 0.1 C, nearly 0.1 C or 0.05 C. Suppose I am charging with 50 ampere charger, right? 50 ampere charger. When the current is decaying up to 2.5 ampere, up to 2.5 ampere. After that, we can cut off our circuit, right? We can cut off our circuit. If suppose you are cutting off your charging at CC mode only, you will not get the full capacity. Means you are only charging up to 90%. Your 10% will be charging on the CV mode only. So that is the main criteria, right? So I hope you can understand this all the phases: trickle charge, pre-charge, constant current charge, constant voltage charge, and the charge termination. Now I am showing you a real-time example. I have actually uh, means with a third-party team, basically we developed a charger, right? EV charger in my previous company. So all the algorithm means this type of, that is nothing but a actually while loop actually we are running inside the program, and we are already sensing the CAN data as well as the hardware data. Means charger having its own hardware as well, right? Voltage sensing means terminal voltage sensing. We are getting all the data from the BMS. We also cross verifying the data with the terminal voltages, right? Suppose it maybe happens that BMS is sending wrong data, right? And we are suppose getting another data. So the charger having its own sensing mechanism as well. The current sensing and the voltage sensing, that is the primary sensing of these chargers. So obviously on this note, means whenever suppose we are sensing this all the datas, obviously depending on this, we are actually changing the algorithm. Means there is obviously we are changing the case study. Depending on the case study, we are changing all the things. One second, I am just sharing with you the flowchart. I hope you can see this screen. Yes, let's see. So see guys, that this is basically a charging profile flow diagram. Now it is basically a 67-volt charger. We are using this charger for a 16S battery pack, 16S NMC battery pack. That means what should be our full charge voltage? What should be? Come on guys. What is the full charge voltage of an NMC cell? 4.2 volt. So just multiply this with 16. That would be nearly around 67.2 volt. Correct me if I am wrong. Right? 67.2. 16 into 4.2. Yes. That would be 67.2 volt. So that means our CV level already we have selected at 67.2 volt. And the charger actually we used, I think 16 ampere. That is a two-wheeler charger. Yes, 16 ampere charger it was. Now the first we are starting from the CAN data validation. Is the BMS is in operating mode or not? If suppose we are not establishing any communication, it will actually don't it will not start the charging. It will go and again in the start phase. So in every 5 seconds, suppose we are connecting the power path, in every 5 seconds it will send a query. If BMS responds on that query, then only it will start the second phase, right? So that is the second phase. If V battery is greater equal to 10%, 10 volt, sorry. If suppose V battery is greater than 10 volt, so for a 67.2 volt battery pack, 10 volt is very less. That means the charger is first verifying the voltage, right? Is it in deep discharge or not? So obviously it is in deep, suppose it's in deep discharge, right? V battery is greater than 10 volt, sorry, less than. Then the charger actually starts for 2 to 5 seconds, and again it will be off for 30 seconds. Again it will start for 2 to 5 seconds, again it will stop. And how much voltage actually it goes up to? Up to 15 volt, right? Whenever there is a 15 volt, if suppose 15 volt have not reached, right, within this trickle charge mode, suppose we have not reached up to 15 volt, on that case it will actually immediately stop the charger, right? I hope you can get my point. from 10 volt to 15 volt, if after this trickle charge technique, if this battery pack voltage is not going on the upper side, obviously we should stop, right? We should stop that. That means there is a problem inside the cells. Maybe it can be uh, mm, it can be short circuited, or anything happens, right? So we should avoid this type of charging, otherwise it will cause the fire cases, right? Now, if suppose 15 volt is achieved, after that it will goes into the pre-charging state, and we have selected I into 0.16, means our 16 ampere charger. So obviously 16 into 0.16, you can obviously calculate how much pre-charging current we have selected. Now this pre-charging current actually goes up to 50 volt. What is the 50 volt? 50 volt is nothing but a nearly around 5% charging. 5 to 10% charge, the 50 volt it is, right? You can actually calculate, if supposed to be that is 50 volt by 16, nearly around 3.1 volt, nearly, that is around 0% charge. So up to 50 volt actually it will pre-charge, it will be at pre-charging state. After that, if suppose there is a 50 volt we get, after that we will start CC1 state. So CC1 state is nothing but a full charging, means fast charging state. So we actually divided this CC state, means constant current state, into a two segment. Means we want actually from 0%, sorry, nearly 3 to 4% charging to 80% charging in a maximum current range. But from 80% to 90%, there will be CC second state, means constant current second state. See, in a firmware, especially in the software, you can control anything. If you properly sense the BMS data, you can control anything. You can control the voltage, you can control the current, right? So that is how actually we are also designing the EV fast charging station. So we are getting the BMS data, right? And BMS is sending, there is a limit in the 80%. Don't go above this current, right? CC current set is supposed to be 100 ampere. So in CC1 state up to 80%, it will give full 100 ampere current. After this 80% state, it will switch to a CC2 mode. That is a constant current mode from 80 to 90%, not 80 to 90. It from 80% to up to CV voltage. Whenever actually there is a matchup between terminal voltage and the charging voltage. If this matchup, on that immediately actually it will switch to CV mode. So you can see up to 65 volt, the current is a full current, that is 16 ampere. After 65, there is a current of 0.6 into I, means we are actually reducing the current. At 67.2 volt, it is actually starting the CV mode voltage, means CV charging, that is nothing but CV charging. And in the CV charging, actually we have set it that the 0.2 should be there, 0.2 into I. That means for a 16 ampere charger, 3.2 ampere should be there. Why we have set it 0.2? 0.2 C, that is nothing but 0.2 C. Actually, the battery pack ampere hour, the capacity, actually 50 Ah battery pack actually we used. So for a 50 ampere hour capacity, 3.2 ampere is very less, obviously less than 0.1 C, right? For a 50 Ah, 5 ampere is a 0.1. So less than 5 ampere, obviously we can stop our charging. So after that, actually we stop the charging. So that is a flow chart. We are actually, this type of CC1, CC2 actually depends on you, the manufacturer, the designer, that how much. Most of the time, what happens? Cell manufacturer also share their current ratings, right? From this amount of SOC to this amount of stuff, suppose to 30% to 80%, you should charge your battery pack with this much current, maximum current. Below 30%, there should be this current. From 80% to 90%, there should be this much current. Above 90%, there should, obviously depending on the cell manufacturer data sheet, you have to select this current rating. right? I hope you can understand this charging profile of lithium ion, right? So this is basically a software part which we have to control, right? Is there any question up to now? Up to now, is there any question, guys? You can ask, because after that we will be starting the hardware based model. What is the inside the hardware actually? We have talked a lot of things, that AC, DC, DC, DC. What actually inside the hardware it is, right? If there is any question, please ask me. You guys enjoyed or not? I think there's a boring class, I think. Huh? Whenever actually we are supposed to deep dive into the electronic segment. Suppose obviously you are many of you from electrical electronics background, many of you from mechanical as well, CS as well, right? So this obviously this type of software algorithm, mechanical guys also should have the knowledge. But whenever suppose we are inside the designing, on that case means mechanical guy also thinks that what we need this, why we need this, right? But yes, guys, for electrical electronics CS guys, obviously this is so much important. Means if you are supposed to going into this industry, right? And for mechanical, obviously there is a task for you also. Whenever suppose we need the outer casing, right? We have to build the IP67 model. For IP67 model, we have to obviously select aluminium die casting. So which grade actually we should select for this charger outer casing, right? You have to work on that, right? How much fins actually we have to select, how we can apply force air cooling in IP67 model, right? I have seen those type of chargers, right? In a compact waterproofing model, we are actually applying a force air cooling, right? Directly connected, means mainly in a charger or in a converter. Mainly the heating element is the MOSFET or IGBT, the switch. So in a IP67 model, they very good carefully design the thermal management of the chargers. They are actually using a fence. They are using a fan, right? DC fan to basically cool the MOSFET surfaces. And this aluminium casing, the overall outer casing actually works as a heat sink. Obviously, our main heat sink will be on aluminium only. Whatever the heat sink we are using, that is aluminium based. So they actually transform the heat sink into an overall outer casing. And obviously, they are using die casting model. So in the die castings, obviously, you can get the IP67 designs. So you have to work on that. Also importing material. So whenever actually we need a very good models from the rusting itself, uh, whatever the mechanical, mechanical strength we have to give. Suppose we are using a onboard charger. On that case, we have to give a mechanical strength. So inside the charger, actually, we are using a potting material, right? So potting material gives you any every kind of safety, right? Rusting safety, mechanical strength. Obviously there should not be any water cases. If suppose we are using IP67, there is a maybe we don't know, there is a chance, if there is a chance of a water leakage, obviously it will protect this potting material. So that type of design, which type of potting material we should select, what should be that thermal conductivity, right? How much watt per meter Kelvin would be there, right? How much watt actually heat wattage we have to extract from the MOSFETs, right? Depending on that, you have to design. So there is a lot of thinking EV, guys. Okay, there is any question? Let me see. In the hardware, we will enjoy. In the hardware, we will enjoy, right? So what does it mean? Means hardware. Hardware means obviously I am talking about the inside the charger model I am talking about. I think you are actually confused. Okay, no issue. Okay, let's come to the charger slide. I am talking about internal charger hardware. Okay, now charging infrastructure. In case of in our India as well as in the overall world, there is a two type of charging actually we are using. One is AC charging and one is DC fast charging mechanism, right? So obviously, uh, AC charging and DC fast charging. In case of AC charging, we used onboard charger, right? There is a in onboard charger. There is a two type of charging. There is a level 1 charging. There is a level 2 charging. Sorry, I'm talking about onboard charger. Onboard charger is fixed, right? Now, in case of level 1 charging in North America, I'm talking about that is 120 volt. Already this is fixed. And in case of level 2 charging in US or in European countries, we are using 240 or 230 volt. So we actually follow the European standards. So that is why actually we are also using 230 volt. The power difference is more. You can see in the level 1 charging, the power is nearly around 1.4 to 1.5 kilowatt. That is very less, right? For a four-wheeler charging, this will take nearly around 20 hours of time to full charge. And you can easily use a regular home sockets. So in case of onboard charger, offboard charger, if we use level 1 charging, obviously it will take more number of hours. Whenever we are using level 2 charging, that is also in the offboard and onboard charger. That is also from 3.7 kilowatt to 22 kilowatt maximum, where the charging time is around 4 to 8 hours. So mostly in the workplaces or any type of supposed to be commercial places, we are actually using this type of public chargers. I think in the highway itself, I think you have seen in many petrol pumps, they are actually integrating this type of charging systems. I mean, I have seen lot of this type of charging stations, right, on the highway itself, on the metro cities as well. In normal highways, in metro cities also, they are developing these things because there are multiple startups actually working on this, especially in the AC charging system. Now there is a another mode, that is DC fast charging. In DC fast charging, it will actually bypass your all the chargers. Means it is directly connected with your battery pack. So there is a DC charging ports is different, right? The AC charging port and the DC charging ports are different. So obviously, I don't know. I think some of the Indian manufacturer giving this DC fast charging, but not in all the models. Okay, we will see the case study. So we that is a level 3 charging, that is rapid charging, or we can say DC fast charging. So the voltage is around 400 to 1000 volt, and the power, guys, 50 to 350 kilowatt maximum. And what is the charging time? That is for 15 to 45 minutes for 80% charging. So whatever we are discussing in the earlier slides, whatever the charging profiling we have seen, so that is based on, means based on that profiling actually, all the DC fast charging can charge your battery pack up to 80%, means up to 80% within this power range, right? So it is actually bypass the onboard charger and directly charge the battery. So DC, obviously, if you have to connect the battery pack directly with this DC, right? It is very common in the highways or the commercial charging station. Now let's come to the type of charging standards. Means the type of charging standards actually depends on the connector. You were developing a charging stations, you were supposed developing a car, right? So on that case, you have to fix your charging standards. Means you have to fix your connector. Whatever the AC adapters actually we are using, that should be fixed, right? In case of charging station as well, in case of EVs as well. So you can see that there is a three types of chargings actually we are using. In type 1, type 2 AC charging, right? In North America, Japan, European market, Chinese market, and also in India. So this type of J1772 actually we are using, right? In case of India also we are using J1772, right? sorry, in European market, we are using IEC 62196. So this type of chargers, connectors, actually we are using in India itself. And there is a different kind of chargers China used, and North America and Japan also use a different kind. And for all market except European country, the Tesla is using their own mode of charging, okay? Because they have their own charging stations, they have their own ecosystem, right? So that are different. Now for DC fast charging system, that is CCS 1. After that there is CCS 2. So for American market, CCS 1 you can see, and for CCS 2. So we are adapting the European market standards in case of AC charging as well as for DC charging. So you can see on the right hand side, there is the Indian market standards. This type of connectors actually we are using. That is specially CCS2 and the second one that is used in Japan. But mostly we use CCS2. In every DC fast charging stations, you can actually see this type of connector arrangement. Right, and EVs also we are using this type of connector. CCS2 connectors are widely, means it is very common, right? So these are the type of connectors depending on the charging standards we are using. Now that is the market analysis, right? So that is the market analysis. In the EV models, I am taking uh, Indian models that are very much, means we are familiar to see, right? Tata Nexon EV. The onboard charger rating is nearly around 3.3 kilowatt, and the AC charging time, which is nearly 8.5 hours from 0 to 100%. So this type of onboard charger, obviously it has the ability, ability to charge from 0 to 100. Obviously there is not a fast charging, there is a slow charging, so we can easily charge from 0 to 100%. But here also we are having all the phases: trickle charge, pre-charge, after that CC1, CC2 and CV. All the modes actually we are operating. In BYD E6, basically we are using 6.6 kilowatt charger, and which roughly takes 6 to 8 hours nearly charging. Now in case of DC fast charger, right, I'm talking about foreign brands. In India, the standard is Bharat DC 001 standard, right? And the voltage is nearly around 48 to 60 volt. And the power output is 15 kilowatt. That is for three-wheeler, two-wheeler only. So we are also developing this 50 kilowatt DC fast charging system for two-wheeler, three-wheeler, especially. From that is Bharat DC 001 standard, right? Voltage range you can easily can see that 48 to 60 volt. Now the four-wheeler segment starting from 25 kilowatt, that is CCS2. Especially you can see everything is CCS2. 200 to 500 volt, the power output maximum 25 kilowatt. That is for mid-size cars. For 50 kilowatt, that is very much common in India. Especially Tata MG is using this segment, 50 kilowatt fast charging system. That is up to the voltage rating is nearly around 200 to 500 volt range. Means your battery pack voltage should be in between range, and obviously the charger should have. After that, there is a ultra fast charging mode. The kilowatt is nearly around 100 to 150 kilowatt. So that is global, means globally it is popular. CCS2 global standard. The voltage range is from 200 to 1000 volt, means 1 kilovolt it can take up to. And it is basically used for premium EVs, right? Premium EVs means in Mercedes actually they are using, I actually forgot the model, guys. I think EVQ3, that type of models actually having. So they are actually using 100 to 150 kilowatt of power output. There is ultra fast charging that is specially for Tesla, Porsche, this type of cars. That is 250 kilowatt to 350 kilowatt. That's a huge power output. And the voltage rating started from 800 volt. And this is a very high end voltage, high voltage battery pack actually we are using. This is 800 to 1000 volt systems actually we are using. It is very rare, and it is basically in European market, and in North America actually it is very popular, right? The ultra fast charging standards. Now for Indian market analysis, how actually we are in, I'm talking about in inside the vehicles. What are the DC fast charging specs actually we are using? For Tata Nexon EV, we are using 30 to 50 kilowatt as I told. It takes 56 minutes and it has a 0 to 80% capability. So it is also using 0%. For MG ZS EV, up to 50 kilowatt, the roughly it is taking 50 to 60 minutes and 0 to 80%. Same for Hyundai Kona. For Tata Tiago, that is actually they are basically that type of SoC range should be there. 10 to 80% they are actually applying the DC fast charging. For BYD, for BYD E6, they are using 60 kilowatt. It is quite higher charging, and it roughly takes 45 minutes from 30% to 80%. So obviously there is a dependency into 30 to 80%. So BYD actually follows the accurate charging mechanism, because I don't think so that we should use this fast charging at 0%. Actually, it will degrade your life, battery life. So that is why actually in our Duham factory, actually I have seen a lot of Tata's battery, MG's battery, second life. Uh, Even it is 3 years back, 4 years back, right? They are giving 8 years of warranty, but within 5 years, actually the battery has degraded, right? So basically they have to improve these things. BYD is following a very good thing, that is 30 to 8% model. So that is the rough market analysis. Now, what is the hardware architecture inside these chargers? Every type of chargers. So obviously there is whatever the chargers actually we named, supposed to be AC charger, DC charger. AC charger is nothing but only having AC filtration only on the AC chargers. Onboard chargers, obviously there is a same hardware architecture we are using. In DC fast charging, also we are using same architecture. Obviously we have to convert the AC to DC, right? Whatever the in general power stations are working on AC, from this three-phase AC we have to convert, three-phase or single phase, we have to convert this to a DC segment. So there is a two type of uh, means two type of conversion is there. One is AC to DC with the help of rectifier. After that, there is a power factor correction circuit actually we are using. It is very, very important in automotive as well as in a industrial grade designs. Power factor correction circuit to basically improve the efficiency of a converter as well as to reduce the losses. Means both are actually connected with each other, right? Efficiency and losses, right? So this power factor corrections is pretty much required. I am not going into really depth into the circuits, right? I'll be showing you a reference design. You can easily follow those designs if you are interested to design a charger, your own charger, right? You can follow those design notes, right? Now, after AC to DC, there is a power factor correction that is also on DC state. 230 volt AC is converted into a 300 or 3 supposed to be 330 volt AC, right? 230 into 1.414 that will be, because in 230 volt AC the peak voltage, whatever the 230 AC, there is a RMS voltage, right? There is a peak voltage we are getting nearly around 320 or 310. So if you multiply with 1.414 into 230, that is root 2, 230 into root 2. So you will get the value, rough idea. And that much voltage actually we are getting after AC to DC rectification. After power factor correction, there is a DC to DC converter, right? You can see that here basically a DC to AC and AC to DC. So this overall thing actually named as a DC to DC converter. This overall, this is a switching element, that MOSFET, right? In power factor correction also we are using switching element. There is isolation, you can see there is a transformer actually we are using. Why? Because of step up or step down. In DC-DC converter, on the next session actually I will be giving you a small brief on DC-DC converters. Because I think you should have a question on that in DC system, in DC-DC converters. Why actually we are using transformer, right? Transformer works on AC. whatever the concept we learned, that transformer can works on AC. Then how actually DC to DC converter we used transformers? That is a different concept. I will be showing you. But yes, for now, there is a DC-DC converters we are using. Why actually we are using DC-DC converter? Obviously, the battery pack voltage is a fix, right? We need a CV voltage, CC CV charging. CC obviously controlled by controller, but CV, at least we have to regulate the maximum voltage, right? The peak voltage. By using this DC-DC converter, this 300 volt, whatever the 330 actually we are getting from the AC to DC rectifier after power factor correction, this 330 volt actually converted into a, means depending on your application, it may be 400, it may be 200, it may be step up, right? It may be step down or it may be step up, depend on your battery pack voltage. So that is the overall hardware architecture, right? Two type of conversions actually we are doing, right? AC to DC, and then we are actually step up or step down the voltages. Okay, so why actually we need power factor correction? As I already told, we have to improve the system efficiency, as well as we have to enhance the voltage stability, right? Whenever, why actually this type of power factor distortion happens? Whenever we are using those diode, right? Diode bridges, and we just use this type of capacitors, that is electrolyte capacitors. On that immediate case, what happens? Whenever suppose we are connecting the charger and we switch on, right? Suppose without connecting, just we are turning on the switch. On that immediate case, capacitor is a, what is the capacitor? So inductor and capacitor is an active element, right? So capacitor stores the charge. Whenever actually we are turning on the switch, it will actually collect a huge amount of current, right? Because it is empty, on empty state. Whenever we are turning on, after this diode rectification, you can see we are using a capacitor for smoothing the DC, right? You can see there is a waveform. After this rectification, actually we are getting this type of pulsating type of DC, right? Pulsating DC. When we use this capacitor in this, after this, it will act, there is obviously there is a small oscillation, but it is negligible. So after using these capacitors, we are getting a nearly pure DC. But these capacitors actually means draw a huge amount of current whenever just we are turning on. So you can see that the current profiling actually changed in AC side. Basically on the AC side, the current profiling actually changed. This type of peaky nature actually we are observing on the AC side, right? Line voltage, line current side. So if we use PFC controller, right? So our main purpose to use this PFC controller to start the current on this state only, right? Obviously there's a power factor concept. Whoever in electrical, electronics especially, obviously I hope that you already know what is power factor, right? There's a difference between in voltage and current, right? Whenever suppose we are transmitting a power, obviously there is a angle difference between voltage and current. That would be the power factor. So mostly in the overall system, we used inductive load, right? Inductive load. So inductive load having lagging power factor nearly around 0.8. Most of the time we take the power factor as a 0.8, right? So I am not going into very deep on that matter, but yes, if we improve the power factor up to 1, so obviously we can extract more active power than reactive power. Reactive power is, there is a two type of power, guys. One is active power, one is reactive power, right? Reactive power is nothing but a loss, and active power what actually we are utilizing, right? So that is our main purpose is, whenever we are improving the power factor, actually we are improving the active power demand, and we are decreasing the reactive power demand. So that is how actually we are reducing the losses. As a result, we are improving the efficiency, right? So that is the main purpose of PFC controller. We are improving the power factor of the circuit, right? So that is the main thing, that is the main requirement of PFC circuit. right? Now, one second. Okay, guys, I think from the next on the next session, basically we will see some V2G G2V technology. Up to now, is there any question? Whatever the charging profiling we have done, whatever the connected arrangement we have done, but obviously the hardware architecture, obviously. So whoever is specially want to means goes into this type of segment, hardware designing, right? So obviously for electrical electronics there is a lot of scope in the hardware designing, but you should have that basic knowledge to be cleared, right? So guys, is there any question related to charging, right? So tomorrow actually I will be starting the V2G G2V technologies because there is a small part actually left. uh, Obviously we will cover that one, and we will cover two important concept, that is the 2 to 3 types of new battery trends which are actually we are running, means research is going on new battery trends, uh, and another one, that is the AIS 156, that is automotive industry standards. So AIS also very much important. What are the standards actually we are using, which type of battery pack certifications we need, so that will be covered on tomorrow sessions. So is there any question, guys? You can ask, please. Okay, there is no question. So I think, guys, then I think we can conclude the session today. So let's meet on tomorrow. So I think we can conclude the session. Thank you, guys. Thank you for joining. Okay, Sushmita, I can end up.
Yeah, sure, sir. Thank you so
Yeah,
much. We'll
thank
meet
you.
again by tomorrow. Thank you, sir.
Thank you. Thank you. Thank you so much.
Yeah, so dear students, kindly mark your